Okay, Chapter 3, Section 3, Projectile Motion. So the basic thing about projectile motion are the key variables. These are very important because these are variables for all projectile motion problems that we know to be true. The first variable is that our acceleration in the x is always equal to 0 meters per second squared. This is because we assume that there are no forces acting in the x and that we ignore air resistance. Therefore, there is no change in velocity. Since our acceleration in the x is 0, we can say that our initial velocity in the x and our final velocity in the x are the same. And lastly, that our acceleration in the y is negative 9.81 meters per second squared. We say our acceleration in the y is negative 9.81 meters per second squared because the only force acting in the y is gravity. And the acceleration due to gravity of any object is always negative 9.81. The negative is because the object, because gravity points downward. So 90% of all problems in this chapter are going to fall into three categories. The first one are launching style problems. Launching style problems, we know that the displacement in the y is 0, the acceleration in the y is negative 9.81, acceleration in the x is 0, and the initial velocity in the x and the final velocity in the x are the same. In this drawing, you can see the path of a projectile moving through its course. So you can see here why the displacement in the y is 0, because the object falls back to the same height that it did in the beginning, or from where it was launched. Therefore, we'd say that the displacement in the y would have to be 0. Number 2, maximum height. In maximum height problems, we know that the the final velocity in the y is 0, the acceleration in the y is negative 9.81, acceleration in the x is 0, and that the initial velocity in the x and the final velocity in the x are the same. In this drawing, you can see the path in max height problem would take, where it would stop at its maximum height. And we would say that the final velocity in the y is 0 because at its maximum height, a projectile won't be moving. It won't be moving in the y, but it will have velocity in the x. And then the last one is something being launched forward, or cliff-style problems. We know in cliff-style problems that the initial velocity in the y is 0, the acceleration in the y is negative 9.81, acceleration in the x is 0, and the initial velocity in the x and the final velocity in the x are the same. So here you can see the path a projectile would take in a cliff-style problem. We say that the initial velocity in the y is 0 because the object is being launched forward and has no component in the y for an initial velocity. It only has an initial velocity in the x. Okay, so first check your understanding. This problem says a projectile is fired into the air and it follows the parabolic path shown in the drawing, landing in the right. There is no air resistance. At any instant, the projectile has a velocity of v and an acceleration of a. Which one or more of the drawings cannot represent the directions for v and a at any point on the trajectory? So the answer is that a and c cannot represent the the acceleration or the velocity of a projectile at any point. This is because for a, it's showing that the acceleration is moving to the right, and since there is no acceleration in the x or acceleration in the x is 0, there can be no acceleration pointing along the x-axis. And for y, it shows that our acceleration in the y is pointing upward. And since we know that in a projectile the acceleration in the y is always negative 9.81, an acceleration in the y must be pointing downward. Okay, so this problem says an object is thrown upward at an angle above the ground, eventually returning to the earth. Problem A, part A asks, is there any place along the trajectory where the velocity and the acceleration are perpendicular? If so, where? And part B asks, is there any place where the velocity and the acceleration are parallel? If so, where? Okay, so the answer for A is yes. when the projectile is at its highest point. At its highest point, as you can see here, since there is no velocity in the y, the velocity will have to point along the x-axis. And since the acceleration is always negative 9.81 in the y, and there is no acceleration in the x, since it's negative, it will have to be pointing downward. As you can see here, those two are perpendicular. And for part B, there is no place where the acceleration and the velocity will be parallel. Here this problem says, is the acceleration of a projectile equal to 0 when the projectile reaches the top of its trajectory? The answer is no, because there is still an acceleration in the y, or acceleration due to gravity, which is always acting on the projectile throughout the throughout the projectile's path. As you can see here, even at the highest point, the acceleration is still there, even if there's no acceleration in the x. Okay, so this problem says, in baseball, the pitcher's mound is raised to compensate for the fact that the ball falls downward as it travels from the pitch toward the batter. If baseball were played on the moon, would the pitcher's mound have to be A, higher than, B, lower than, or C, the same height as it is on Earth? Well, we all know that the gravity on the moon is much weaker, or it has a less magnitude than it does on the Earth. Therefore, we would say that the that the pitcher's mound would have to be lower, because the acceleration due to gravity of the ball will have a smaller value. Therefore, it will take longer for the ball to fall to the ground in a sense. So here we're going to show baseball on the Earth. This is basically the path that a baseball will follow on Earth. As you can see here is the raised pitcher's mound, which is falling to the ground. So the ball, because the acceleration due to gravity on the Earth is much higher than on the moon, the fall will be a lot more drastic and a lot faster. But on the moon, since the acceleration due to gravity is less than on Earth, the ball will fall to the ground over a much longer amount of time. Therefore, it won't take as high to reach the same point. So question 7 says, a tennis ball is hit upward into the air and moves along an arc. Neglecting air resistance, where along the arc is the speed of the ball, a minimum and a maximum. Here we can see the projectile that a tennis ball would follow. So we would say that the speed of the ball at its minimum would have to be where the ball is at its maximum height, because as we know, at the maximum height of any projectile, the velocity in the y is equal to 0. Therefore, it only has a component in the x, and the maximum would have to be either in the initial and the final position of the projectile, because if an object were to slow down, its initial position would be the fastest, but if an object were to speed up, its final position would be the fastest. This question says, a wrench is accidentally dropped from the top of a mast on a sail. Air resistance is negligible. Will the wrench hit at the same place on the deck whether the sailboat is at rest or moving with a constant velocity? So the answer here is that yes, the wrench will hit the same place whether the sailboat is at rest or moving with a constant velocity. This is because the wrench will always have the same x component of velocity as the boat, because before the wrench falls, it's moving in harmony with the boat, but once it falls, it still retains that x component of velocity of the boat. This problem says a rifle is at height h above the ground fires a bullet parallel to the ground. At the same instant and at the same height, a second bullet is dropped from rest. In the absence of air resistance, which bullet, if either, strikes the ground first? So the answer here is that both bullets will strike the ground at the same time. This is because the bullets have the same acceleration, they have the same distance from the ground, and they're both starting from rest. Therefore, they have pretty much the same components, and were you to plug in some values for their for their kinematic equations, you would get that they would strike the ground at the same time. Okay, so question 11 says a leopard springs upward at an angle of 45 degrees and then falls back to the ground. Air resistance is negligible. Does the leopard at any point on its trajectory ever have a speed that is 1/2 of its initial value? So the answer is that no. And this is because at a 45-degree angle, both its x and y components of the initial velocity are going to be the same. And at the point where its velocity would be at its minimum, or the least, which is at its highest point, because the y component of velocity is 0, its velocity is still higher than 1/2 of the initial velocity. So in order to make this easier, we'll do an example, and we're going to plug in values. So we have the initial velocity is 5 and the angle is 45 degrees. So we would get that the initial velocity in the x is 3.53 and the initial velocity in the y is 3.53. And because this is a max height problem, we would say that the final velocity in the y is 0 meters per second. Then in order to find the velocity of the object at its highest point, we would do the Pythagorean theorem, and we would do that 3.53 squared plus 0 squared. The square root of that is still 3.53, which is greater than 5 divided by 2, which is half of the initial value. So that's why we would say that an object, even if an object is at its highest point, its velocity will still be higher than its initial velocity if it's fired at a 45-degree angle.